So the project title is Microwave Metamaterial Absorber for X, C and KU band applications. So before starting to the design, I am going to start with the question, why microwaves? So the microwaves are millimeter waves. It is occupies the wavelength of 32 0.03 centimeter, and it is lies between 10 to the power 9 hertz to 10,000 gigahertz, and it provides the lots of applications in to design by antenna, filters and absorbers. This region is completely occupied with different types of devices with applications, and this interior design of microwaves having the several types of bands with some different types of frequency values. So with the different types of frequency ranges, the interior microwave band is splitted in different types of regions. So the first one is L band, then S band, C band, X band, KU band, K and KA band. So because of these frequency regions, we splitted the bands like this. So we need to cover the L band, S band, C band means we need to design the antenna between 1 to 5 gigahertz. So the frequency range is 15 to 20 gigahertz means it will cover the KU and K bands. So in our case, we will design the we will design the metamaterial absorber in X, C and KU band applications. So this is the importance of microwaves. It provides the higher bandwidth and lower diffraction, and it provides the better line of sight communication. And here metals can be used as a perfect electric conductor, and it provides the fast and secured communication. And here the better penetration depth and less scattering rate too. So this is the microwave band's interior range. Here the L band is having the frequency range is 1 to 2 gigahertz, and the frequency range is 8 to 10 gigahertz means it's a X band. So this is the corresponding band values with the frequency ranges. This is the totally this table is the microwave bands. So first of all, introduction. Here in this project we are going to design the metamaterial absorbers. First of all, metamaterial is a artificial materials. Okay, this is engineered to provide the properties which are not readily available in nature. This structure usually gained their properties from the structure rather than composition. The design parameters include physical construction, material and geometry. Compared to the natural materials, this metamaterials provides the negative values of permittivity and permeability simultaneously. So that is the artificial materials. So and the characteristics of electromagnetic waves used to analyze the different types of functional devices for different advantages, including modulators, filters, antennas, the slow light effect, cloaking, and electromagnetically induced transparency and phonoresonance. And generally the metamaterial absorber having three layers: top resonator, middle dielectric substrate and bottom plane. Okay, so the dielectric substrate is placed in between the bottom ground plane and top patch. In general cases, top patch and bottom metal used here is copper, and the middle dielectric substrate is FR4, because we are choosing the region microwave. In the microwave regions of applications, FR4 will support. So this is a literature survey. The first paper is a polarization controlled and flexible single and pentaband metamaterial absorber. So in this case, the only one absorber gives the two different types of operations: single band and pentaband. Penta means 5. So single band and 5 band. So the metal used here is copper and the substrate used here is Teflon. Okay. And they are achieved the 99.8 percentage for at 6.64 gigahertz for single band of operation, and more than 99 percentage achieved at 5 different frequencies, and a Teflon substrate is used. And the second paper is photo excited switchable single and dual band metamaterial absorber. So in this case, the author used the three different layers, and with two different types of substrate. Here they used silicon and polyimide as the substrate, and gold is the metal. So gold is the metal, so it definitely increases the cost. And additionally, instead of using the one dielectric layer, they are using the two different dielectric layers, so it increases the multi-layer structure. So it increases the chance to fabricate the design difficulties. And the third one is ultra subwavelength thickness for dual and triple band metamaterial absorber with very low frequency. So here author designed the two different operation for dual band and triple band by adding. Here they are adding and the lumped capacitors to the basic metamaterial absorber. And ultra thin triple band metamaterial absorber is also realized and investigated in the radio band. So they are using the capacitor structure for achieving the absorption rate. And the fourth paper is design of narrow discrete distances of dual triple band metamaterial absorbers. Here a narrow discrete distances of dual band Dirac absorber based on two pairs of gold strip and dielectric layer backed by gold film is designed. Also, it demonstrates two different narrow discrete distances of a triple band absorber through stacking one more pair of AU strips. So, mainly author mostly used the stacked layers of operation. Stacking means different multiple layers are arranged in a single metamaterial absorber structure. And this paper is showing single and dual band absorber, metamaterial absorber in flexible polyimide substrate for three different frequencies, 77, 95 and 110 GHz. So here the ultra thin millimeter wave absorbers on flexible polyimide substrate utilizing metamaterial absorbers were implemented for single and dual frequency bands in an emerging frequency spectrum of 77, 95 and 110 GHz. The dual band absorber implemented in this research uses two resonators, one embedded inside the other. So it is a stacked layers mechanism or multiple layers in a single unit cell mechanism. So the existing method from the literature survey, the existing method is authors mostly used multiple resonators in a single unit cell or multiple layers, which means stacked layers, layer by layers, one layer then top of the another layer and top of the another layer. So mostly multiple layer structures or multiple resonators in a single unit cell is used to achieve a absorption rate. Okay, so or doping means adding impurities to the structure. So the three different points showing the this point discussed about these points only. So stacked layers or multiple resonators in a single unit cell are doping. So without using this technique, we will develop the metamaterial absorber in our proposed method. So we will design the metamaterial absorber without using stacked layers or multiple resonators in a single unit cell. So it provides the easy method for fabricating the absorber structure. So this is our flow chart. First of all, we need to choose a material. So the material used here is copper and FR4 dielectric substrate, and choosing dimensions, that is geometrical dimensions, and boundary conditions and frequencies values we need to fix. And after this the design is simulated by using CST Microwave Studio software, and some output we will take from CST software. So this is the proposed microwave metamaterial absorber. So the perspective view, front view and back view of the absorber is shown here. So these are all the some initial steps from CST Microwave Studio software. So the first of all, we need to fix the background properties, and the background is always set is normal while designing the metamaterial absorber structure, and the microwave frequency units is millimeter and gigahertz, and time is nanosecond, and temperature is Kelvin, because we are going to design the absorber in the microwave region. So we need to choose, and gigahertz is the microwave frequency range. And boundary cell conditions, we need to choose the boundary in unit cell boundary conditions in x and y directions, and open space boundary condition we need to choose in z directions while choosing the Dirac metamaterial absorber structure. And this is the creating a front and back copper layer and fourth substrate. So this is this one is explaining the three different layers forming method. So the bottom layers having the -6 to 6 mm, and the thickness is 0.8, and substrate having the thickness is 0.8 plus that remaining patch value. So this picture shows the ground plane, bottom plane and dielectric substrate thickness values. And this window shows the modeling the shapes. So from these shapes we need to pick whatever the shapes we need to pick from this shapes tab. So here the circular shape, cylinder shape, square shape, cone shape, whatever we need, we will choose from these shapes. And the next one is initial condition settings like millimeter, gigahertz and picosecond Kelvin. So these and all we need to choose before starting the simulation. And in the boundary condition, x minimum and y minimum is chosen as unit cell in the x and y direction, and z is chosen as open and add space for set directions. And the material properties is material type is always normal while designing the metamaterial absorber structure. And the frequency range is 5 to 16 gigahertz. In this particular metamaterial absorber is resonated between the 5 to 16 gigahertz. So we fix the frequency range here. And this is the proposed microwave metamaterial absorber structure, and the dimension is shown in this table. So the L and W represents the copper bottom plane thickness. So 12 cross 12 mm, and substrate length and width is 1.9 into 2 mm, and the radius of the circle is 0.5 and 2.5 mm. So it is all measured and shown in this figure. Bottom layer thickness is 0.035 mm and top layer thickness is 0.035 mm, and the FR for middle layer dielectric substrate thickness is 0.8 mm. Why we are choosing the 0.8 mm means it is all readily available in products. So commercially it is available. So we are choosing the FR for as 0.8 mm. And this is the general proposed metamaterial absorber structure layers. So generally the metamaterial absorber having 3 layers: bottom ground plane, dielectric substrate and the top patch structure. While designing these 3 layers, the top patch structure design method is very difficult because it is you need to fulfill the impedance matching condition with the environment and also achieved to zero reflection and resonant frequencies. And the metallic ground layer blocks all the incident electromagnetic waves. The second dielectric layer is a spacer used to dissipate the electromagnetic wave. So this picture shows the output absorption rate curve. So we are going to design the metamaterial absorber. So the name in the sense we identify the absorber. So it gives the absorption rate, right? So metamaterial absorber. So how much amount of absorption rate we achieved from that absorber. So that one is analyzed from this graph. Okay, this picture shows the absorption curves in terms of wavelength. So 3 different frequencies we achieved, and this picture shows the 3 different frequencies absorption rate. So nearly we are achieved 99% for 3 different frequencies. 5.7 gigahertz, 15.2 gigahertz and 15.8 gigahertz, and the corresponding absorption rate is 99.7 and 95 and 99.9 gigahertz, 9%. And bands in microwave is if the frequency range is 5.7 means that is C band, and 15.2 means also C band, and 15.8 means KU band. So this is the absorption rate of frequency for TE mode, and the TE mode this one and TM mode is this one. So both the TE and TM mode, the absorber is resonated at same frequencies with the same absorption rate. So it is polarization insensitive in nature. And this is the return loss curve. Here we achieved nearly minus 25 dB and minus 20 dB return loss. So it will increase us the chance to get absorption value as 1. So this picture shows the theta value for different angle values. Theta is the incident angle. So while choosing the incident angle theta value, the structure gives the same output for all the 3 different frequencies. So it is polarization independent in nature. And this is a different polarization angle pi. So while varying the angle values from 0 to 90 degree, The absorber gives the same absorption rate for 3 different frequencies, so it is polarization independent absorption performance, which means while we use the absorber for different frequency of operation in the open space like 0 degree, 90 degree, 30 degree, whatever, we need to achieve the same absorption rate for all the frequencies. So it is done by using changing the angle values of theta and pi values. So this picture shows the electric field distribution curves for 3 different frequencies. So the electric field and the electric field intensity calculator is shown in the side of the structure. So red is the maximum and the second maximum is yellow and green. So in our case, the electric field is maximum occupies the patch structure and some of the dielectric places. Because the green is available in the top of the patch structure and some places in the surface of the dielectric. And this picture shows the magnetic field distribution. Actually, magnetic field distribution is very good in this structure because it mostly covered by yellow, red and green values. So the magnetic field distribution is better in this frequency range. And this picture shows the surface current distribution. Here also the surface current distribution is maximum at the top of the patch structure, and the corresponding frequency ranges with absorption rate is shown in this table. So this is the simulation output inferences. So our main objective is to design the absorber without using the multiple layers or multiple resonators in a single unit cell. So we achieved here because we are using only 3 layers, 2 copper layers and 1 FR4 layers. But in the literature survey, authors mostly used many layers. So by using 3 layers, we achieved the 3 different bands, 5 to 16 gigahertz, and averagely we got 99% of absorption rate, and return loss is below minus 10 dB. All the graph works are drawn by using Origin Pro software. So the conclusion, the main importance of multiband metamaterial absorber and microwave region is explained, and the absorption rate and the reviews about the multiband absorber is explained, and the microwave applications, return loss, electric field distribution, magnetic field distribution, surface current distribution, and the polarization and incident angle mechanism plots are drawn by using CST Microwave Studio software. And the targets works, actually we need to increase the number of bands because we got only 3 different bands here. So in order to increase the number of bands, we need to study the parameters. So then the parameter studies process is going, so to achieve the maximum number of bands. So the application, so it is used in the electric toll collecting service, near field lithography with the extraordinary transmission, then photonic crystals, sensors, importantly sensors, acoustic metamaterial absorber, imaging, selective thermometers. In the sensors case, it is used to identify the RNA and DNA molecules in a blood. So it is mainly used in the sensor applications currently. So these are all the references. Thank you.